Hello everyone, today I will be presenting our research on Windows Kernel streaming from this year. I am Angelboy. Currently, I'm working as a senior security researcher at DevCo, focusing on vulnerability research. I was also recognized as a Microsoft MVR this year. Today, I would like to show how I discovered these vulnerabilities. For vulnerability researcher, looking at historical vulnerability is indispensable. When I start hunting for vulnerabilities, I usually begin by reviewing past patterns to identify potential areas to focus on. Initially, we would like to target Win11 in Pontoon this year. Therefore, we decided to review past Pontoon events and the recent in the wild vulnerabilities. Let's briefly mention some of the common targets exploited by hackers. First one is Win32k, which has been a hacker-based friend for over a decade. It's used whenever you interact with graphical interfaces. Since these components are complicated, it's no surprise they contain numerous vulnerabilities. Next is CLFS, which has become very popular over the past 6 years. It's used for handling log file systems. Naturally, this means there is also a lot of complex code, making it one of the popular targets on Windows recently. The last one is MSK SSRB, a new target from last year. It's a kernel streaming service for general multimedia devices, allowing multiple processes to show the same device. Unlike the previous two, it's very small, and you can review the driver in just a few days. After a Pontoon event last year, it became a favorite target for hackers. Within a few months, two vulnerabilities were widely exploited. However, becoming familiar with Win32k and the CLFS require more time, and many researchers are already examining them. Therefore, we decided to focus on MSK SSRB for historical vulnerability analysis, hoping to identify other potential vulnerabilities. Let's take a look at the past vulnerability in MSK SSRB. The first one is used by Synaptive in Pontoon last year. It is a logical vulnerability. When the kernel uses the API to map memory address provided by user, it does not correctly set the access mode flag. This leads to the failure to check if the address belongs to user space. If the user provides a kernel address, it will map the kernel address to user space. As a result, the user can do arbitrary memory writing in kernel space. The exploitation is straightforward and stable, making it the type of vulnerability favored by APT groups. Next vulnerability in MSK SSRB is CB24 It stores the internal object in the file object for subsequent process. However, when used, there is no type check on the structure, leading to type confusion. For detailed information, you can refer to Chompi's article on IBM X-Force blog. This year, Chompi also discovered a UF vulnerability in MSK SSRB. She successfully exploited it during Pontoon this year. It is also very interesting, but I will not discuss it here. I recommend everyone to check it out. However, the MSK SSRB can be reviewed in just a few days, and the 3 vulnerabilities have already been discovered. Many researchers have already thoroughly analyzed it. Does this mean there are no more bugs? Actually, MSK SSRB is just the tip of the iceberg. In fact, there are many other potential components. The one listed in the diagram above are all part of kernel streaming. You frequently use them. You frequently use this in your daily life. For instance, the video driver used for video call, the audio driver used for listening to music, both fall under the scope of kernel streaming. After playing with the kernel streaming, numerous vulnerabilities were eventually discovered, following like a string. Okay, let's play it now. So what is kernel streaming? On Windows system, when you open a webcam or open audio devices, such as microphone, the system needs to read or write related data, such as your voice, and capture image from your device into RAM. It is essential to read data into your computer more efficiently. Microsoft provides a framework called kernel streaming to handle this data. In kernel streaming, three multimedia class driver models are provided: Pole class, AV string, and the stream class. Pole class is used in audio drivers such as your volume control. AV string is mainly used for video-related purposes such as your webcam. Stream class is outdated and rarely used. We won't go into detail here. If we want to interact with devices like webcam on Windows, you need to create a device such as like any other device. For example, open a device and then use IOCTL to interact with it. However, something a bit special here. We need to list devices to see which devices are available in your computer first. These names are not typically like normal device name, but rather something like this one. Each computer is also different. Microsoft provides some setup serious API to help you list the devices you need. Case also provides its own API to do this. Actually, this is just a wrapper that combines setup API and a create file. After we open this device, kernel will create some kernel streaming related instances, which are kernel streaming aperture. This instance will be frequently used, mainly to encapsulate the hardware functionalities of device for developer. Among them, the most important are kernel case filter and the case pin. Case filter usually represent a device or a specific function of a device. When we open an audio device, in most cases, it corresponds to a case filter, which is a green box in a diagram. When reading data from the audio device, it is read into the filter from the left, processed through several nodes, and then output from the right. It usually ends up in your RAM. The point for reading and writing data are called pins. Each of these case objects have its own property, and each property corresponds to a feature. For instance, the data format in a pin, the volume level, and the state of the device are all properties. These properties typically correspond to a set of GUID. We can set this property through IOCTL case property. For example, if you want to set the device state, you can directly send an IOCTL request along with the GUID to the device. You can also use this IOCTL to get information about the current volume level. After understanding of the functionality and the operation of kernel streaming, we need to understand the architecture and how Windows implement it to find vulnerabilities. It will guide us in determining where to start. Following our analysis, the overall architecture looks like this diagram. After you send an IOCTL request to case device, these are the drivers that might handle your input. Let's talk about case trunk first. Case trunk is the entry point in kernel streaming. It converts 32-bit requests from the WAL64 process into 64 requests, allowing the underlying driver to handle the request without additional processing for 32-bit structure. Another one is case, which is one of the core components of kernel streaming. It is the library of kernel streaming responsible for forwarding requests, such as IOCTL case property to the corresponding device driver, and it It also handles function related to AV string. Here we can explain the process of sending a case IOCTL and the driver it actually goes through. First, the application sends an IOCTL to the device, and the IOCTL will be forwarded by the IO manager. Since it is sending an IOCTL to the case object, it will be handled by case trunk first. It will check if the request is from a 32-bit process here. If not, it will pass it down. Assuming you are sending a request to an audio device, it will be passed to the audio filter first. By default, the audio filter will pass the request downward and notify case about which property it supports. Case will check if the property set that the user wants to set is supported by the device. If a device supports it, it will pass to the corresponding property handler in the audio filter. As shown in the figure above, it is forwarded to the handler in a port class to operate device. Now, you should have a basic understanding of the architecture and the process of kernel streaming. Next, it's time to look for vulnerabilities. Based on the information, which attack surfaces are worth examining? First, each device and the case object has its own property, and each property has its own handler. Some properties are prone to issue during handling. Second, case and the case trunk have had no vulnerability for a long time, and the code quality is not good. They are the most accessible entry point and might be a good target. Third, in some functionalities of kernel streaming, some drivers handle part of the input individual, which may lead to inconsistency. After reviewing kernel streaming from this point, we quickly identified several vulnerabilities within a few days. Most of these vulnerabilities are obvious issues, such as unchecked size to outbound access or integer overflow. For example, in the entry point case trunk, when reading the size of the user buffer, the size is not correctly checked, leading to an integer overflow. The attacker can use this vulnerability to trigger a pool overflow for future exploitation. There are also many bugs like this one. Due to time constraint, we will not be explaining this vulnerability one by one. During the review process, we discovered some interesting things. In the entry point case trunk, we found this code snippet. Do you think this piece of code is really fine? If you have been researching on Windows, you should frequently see similar snippets. You will see that after checking a request mode, some dangerous operations are performed. However, in normal case, it is safe. When you call system call from a user application, request mode will always be 1, indicating that the call is coming from user mode. We need to mention an overlooked bug class and a few terms first here. In a user application, if a user operates the device through an NT call, the kernel will mark the previous mode in the thread object as user mode to indicate that the system call is from the user. If you call the LDW system call from kernel mode, such as device driver, it will be marked as kernel mode. Another similar field is the request mode in the IRP. This field records whether your original request came from user mode or kernel mode. Usually, it is copied from a previous mode. It's often used to decide whether to perform additional check on user requests, such as memory access check or security access check. But there are some issues in some cases. James Forshaw mentioned a type of bug class. Under normal case, when we call open file or other NT call, the kernel will set the previous mode to user mode. However, what if the driver call LWopen or other LW0 system call? At this point, the previous mode will switch to kernel mode. Moreover, during the second call to open file, if the handling driver use our input as parameter, due to previous mode being kernel mode, it will bypass most of the check, such as SS check. Additionally, IRP request mode will also switch to kernel mode. There might be issue if it relies solely on request mode to decide whether to perform check. However, this research mainly focuses on LW0 system call. You can think about it here. Are there other similar situations that could also cause this kind of logical vulnerability? The answer is yes. I/O build divide I/O control requests will also cause this same issue. It is one of the methods used by the kernel driver to call divide I/O control. It helps you to build the IRP. When using this API by default, the request mode will automatically be set to kernel mode. It is very likely that developer may overlook this remark. After a quick review of this bug pattern in kernel streaming, we found something that caught our attention. This API is used in case synchronous I/O control device, and it invokes IOCTL in the kernel using the aforementioned method. However, it seems that request mode is correctly set here, and the different values are assigned based on the parameter of the function. This will be a convenient library for case driver developer. But we found that in kernel streaming, all code using this function consistently use a fixed value 0. This means using kernel mode to call IOCTL, such as this one, and this one. I have not seen a non-zero one yet. Therefore, we convert the bug pattern in kernel streaming into the following point. The first is the code that calls this case function and set it to kernel mode. The second one is to be able to control part of the input buffer and output buffer. The last one is handling the second IOCTL, which relies on the check of previous mode and has a primitive that can be used for EOP. For example, after check request mode, using the user provide address for writing. After reviewing the code in case, we quickly found an exploitable vulnerability. The first vulnerability is the one I used in Pontoon this year. In the IOCTL case property of kernel streaming, unserialized safe require allow user to operate on multiple properties within a single IOCTL code. It is increasing efficiency. This part is important in case. You can see that when it's handling property in case, if the unserialized safe flag is provided, it will use unserialized property set to handle your request. Let's take a look at unserialized property set. You can see that during the processing, the original request is first copied into a newly allocated buffer. Subsequently, the buffer is used to call a new IOCTL using case IOCTL. But here we can see that the request mode for the IOCTL is set to kernel mode. Moreover, both input buffer and output buffer are controlled by us. Let me use some diagram to show the workflow of unserialized property set. First, we send an IOCTL to interact with the audio device. At this point, the request mode will be user mode, and it will be handled by case trunk and or direct forward it down here. After sending it to the audio filter, if it is a case property request, it will be handled by case. Case will check whether the property set we provide is supported by the audio filter. If a property is poor and is set with unsure set flag, unsure property set will be used to handle this property. Case will call IOCL one by one according to the content of the property set. At this point, the new IRP request mode will become kernel mode, and the subsequent processing will be same as the normal case. As a result, we have a primitive that allows us to perform arbitrary IOCL case property with kernel mode now. Next, we need to look for targets that might allow us to achieve EOP. The first thing you will likely notice is the entry point case trunk. Do you remember the previously mentioned code snippet? It is located at case trunk, and as long as it is a 64-bit request, this function will be executed. In this function, under normal case, when the user uses device control, an error will be returned because request mode is user mode. However, since we are going through the case device IO control, the request mode will be kernel mode here. It will not return error. At this point, user input will be directly used as a function call, and the first parameter is controllable. But we must ensure that property set is DRM audio stream before this special handling. Luckily, both the port class and the DRMK device have these properties. As long as you have a song card, it will meet the condition. After writing the POC, we confirm our result. We have an arbitrary code with one argument now. The next step is to achieve EOP with arbitrary code primitive. It should not be too difficult for this situation. Although you will encounter some protection such as KCLG, KSOR, and SMEP. But under media integrity level, the only thing that you need to handle is KCLG. You can use anti-query system information to bypass KSOR before 24H2, and reuse kernel code to bypass SMEP. Our goal here is straightforward, to create an arbitrary writing primitive for a value function, which can then be used to achieve EOP through typical method. Now, we are trying to write stuff, so let's look for set function. Because when setting value, we have a good chance to write stuff to memory. We directly take the explore function from NT kernel to see if there are any good gauges. These functions are generally valid. There are a few function names that contain set. At this time, we went through them one by one to see which one meet our requirement. 2 hours later, we quickly found RTL set all bit. It seems to be a very useful gadget and a value function in KCFG. Moreover, it only needs to control one argument. We can assign the buffer to any edges and set the size, allowing us to set up a range of bits entirely. We can set all bits in arbitrary memory now. At this point, we are almost done. We can use this primitive to set all privilege of the process token to FFFF, and you will get all privilege. There are many methods to achieve EOP. I use the most common approach by leveraging the SE debug privilege. It allows opening high privilege process such as WinLogon to perform EOP. Finally, we successfully exploit Win11 on both physical machine and VMware. This is like a proxy using the kernel as a proxy to call IOCTL, resulting in a logical vulnerability. However, before the Pontoon event, we create a new VM on Hyper-V and ran the exploit. The result was failure. It failed at open device stage. After looking into it, we discovered that Hyper-V does not have an audio device by default, causing the exploit to fail. In Hyper-V, only MSK SSRV is present by default. However, MSK SSRV does not have disseminate property, which prevents us from triggering the vulnerability. Therefore, we decided to review the entire process again to see if there were any other exploitable vulnerabilities. As a result, we have found another vulnerability. After re-examining it, it was found that case property used nature I/O to transmit data. It means that it used the input buffer for data processing directly. Generally speaking, this method is not recommended as it often leads to double fetch issues. From the above diagram of case property handler, we can see that after the user call IOCTL, the user input is directly copied into a new buffer. It contains property GUID. This GUID is then used to check if the property set is supported by the device. If it does and the set unserialized flag, it will process to call unserialized property set. Let's take a look at unserialized property set again. It copies the user data from the user buffer once again, and then use it as input for the new IOCTL. Clearly, there is a double fetch vulnerability. Let's go through the workflow again. First, our exploit makes an IOCTL call to the MSK SSRV device. During case property handling, case will copy the user input to kernel memory first. The property GUID is the kernel memory the property GUID in kernel memory will be used to check whether the property is supported by MSK SSRV. It is support. If it is support, it will call unserialized. During unserialized, the property will be copied once again from the original user input buffer to the kernel buffer. However, we can trigger the double fetch vulnerability by using another thread to replace it. This will cause the property to become disseminate audio string. At this point, disseminate property set will be copied to kernel memory buffer. Finally, case will use this property to do IOCTL case property. Then we can change back to the original exploit. Let me show it here. I use the version from May this year, and use a normal user. Then run the exploit directly. You will get system. Furthermore, this exploit has never failed to run, and it actually worked from Win 7 to Win 11. Finally, we successfully compromised Win 11 during Pontoon this year. Is that the end of it? A few days later, we found a second vulnerability using the same method. Now, let's talk about the second vulnerability. This vulnerability is in another IOCTL case event. Case object not only has its own property set, but also provides the functionality to set case event. For instance, when the device state changes or at regular interval, you can set an event to trigger. Each device or case object similar to a property has its own event set. To use it, the device must support it. We can register this event by using IOCTL case enable event. You can provide event handle to it. If the event trigger, it will notify you using the handle. When calling IOCTL case event, if the process is a 32-bit process, it will also convert the 32-bit request to a 64-bit request. During the conversion process, you can see similar bug pattern, copying the user input to the kernel buffer. And then use this kernel buffer to call new IOCTL. Request mode is also set to kernel mode. Now, let's go through a few diagrams again. First, use a 32-bit process to call IOCTL case enable event. Initially, the request mode is user mode. The request will be converted from 32-bit to 64-bit here. After conversion, it will call IOCTL in case. At this point, the new IRP request mode has become kernel mode. We can do arbitrary IOCTL case enable event with kernel mode now. Next, we need to find a target to EOP again. But we didn't find a suitable target in case chunk. So we decided to pass it down to look for another target. We shift our eye to the next layer case to see if there are any chance for EOP during the event handling. Quickly, we found a place that's called our eyes. We found that it checked the request mode in the enable event handle first. At that time, we wondered why it was written this way. In fact, if you call IOCTL case event from a kernel driver to increase efficiency, you can directly provide an event object or other kernel object rather than providing an event handle to register the event. That is, we can use the kernel mode IOCTL primitive to provide kernel object to it. There is a chance for EOP, but it depends on how this object is used later. Although there are some things that need to be handled here, I will skip over them for now. You can refer to our blog for more detail later. When will it use the case object that you provide? When an event is triggered, case will call case generate event through DPC. It will use the kernel object to do something. There are multiple ways to exploit it. We chose a simple way, case work item. We can pass a kernel pointer. It will use it as case work item object. It can achieve an arbitrary increment. So we have arbitrary increment primitive now. From arbitrary increment primitive to EOP, there are many methods that can be used, such as abuse token privilege on or IO ring. It seems trivial, but if we use the method of abusing token for EOP, we need to override token multiple times. It may take a long time and not stable. Using IO ring to achieve arbitrary write might be a simple method. Only need to trigger the bug twice. However, a problem arises. When triggering the arbitrary increment, if the original value is 0, it will call case Q work item. It will use some field in IO ring, leading to BSOD. It seems to be stuck. Is it really impossible to exploit it in a stable way? Okay, let's find a new way. We decide to choose to derive new idea from current method. We beg to take a look at abuse token technique. The goal is to get SE debug privilege, allowing us to open Windows Kernel process. There is a question: why does having SE debug privilege allow you to open Windows Kernel process? We need to take a look at PS open process first. From this code snippet, we can see that when we open process, the kernel will use SE single privilege check to check if you have SE debug. If you have it, it will be grant process all access permission, allowing to perform any action on any process except PPL. However, it is worth noting that NT-SE debug privilege is a global variable in NT kernel. It is initial at system startup. The actual value is 0x14, indicating which bit in privilege field represent SE debug. Therefore, when we use NT open process, the kernel will read the value in this global variable to see which bit of the token privilege to check. Next, it will use the value to validate the current process token to check if it has required privilege. However, there is an interesting thing. The global variable is located in a writable section. A new idea was born. By default, a normal user will have only a limited number of privileges, as shown in this diagram. We can notice that in most cases, SE change notify privilege is enabled. At this point, we find that SE change notify is 0x17. How about use the vulnerability to override the value of SE debug privilege to 0x17? As shown in this figure, in the NT-open process flow, it will first get the value of NT-SE debug privilege, and at this time, the value is 0x17. The next check will verify the current process token using the value to see if it has this privilege. However, normal users generally have this privilege, so even you don't have SE debug privilege, you can still pass the check and get process of access permission. Okay, let me show it again. Finally, we also develop an exploit for the second vulnerability. And I use the same version, same user under media integrity level. And create two processes. One is 32-bit to trigger the vulnerability. And trigger vulnerability 3 times, it will override NTSC debug from 014 to 017. And you will get a system again. Okay. We have achieved another proxying to kernel. After Pong2On, MSRC patched this vulnerability a few months later. However, for the proxying part, they simply block the DRM property. Is this really enough? Could it be possible that finding other exploitable property might bypass this? Maybe you can try to figure it out. The next, let's talk about what else can be done with this attack surface and bug class. For this type of vulnerability, you need to pay attention to the timing of setting request mode. If it is set to kernel mode and then user input is used, there might be issues. Moreover, this type of vulnerability is often very exploitable. In kernel streaming, I believe there are quite a few potential security vulnerabilities. There are also many components like HD audio or USB video that might be worth examining and are suitable place for fuzzing. Takeaway: when doing vulnerability research, it is indispensable to learn from past vulnerabilities and understanding previous research. Also, it is the same for exploitation. When current exploitation methods no longer work, explore the core mechanic. You may discover new approaches. Is that the end of it? In fact, apart from proxy-based vulnerabilities, we have also identified many other bug classes, allowing us to discover over 20 vulnerabilities in kernel streaming. If you are interested in this vulnerability or bug class, we will publish them in our blog. Thank you for listening.